Welcome back. So what we are going to do in this lecture today is basically two things. The first thing that we are going to do is how do we set up standard machine learning problems in case of materials informatics. And for this part, just to keep it simple, we are going to work with only this intrinsic property or this composition dependent type of thing instead of something that brings in the microstructure. So after we see how we do the setup for different types of machine learning problems and materials, we will then go to the next part and discuss how we can actually use the concepts that we learned in the previous lecture when we were talking about SHAP and PDP and IC and Cosmo in order to interrogate these machine learning models, make them a little bit more explainable and understand the decision making process that goes on behind the scenes. So let us start with a toy problem. So I'm just writing out the problem over here for you to see, and basically you are being given a data set with alloy compositions and liquidus temperatures. So this does not have to be a single alloy system. This can actually be quite a different bunch of alloys. So you might be having something in the copper nickel domain, you might be having something in nickel silicon, you could be having silicon germanium, whatever it is. So you have a data set with a bunch of different alloy compositions, and then your target value is basically the liquidus temperature. So based on this, you are asked to develop a machine learning model which can predict the liquidus temperature of any alloy composition. So when you tackle a problem like this, the first thing you need to understand is what features would you actually use in this model, and then because you want to do the feature selection using the concepts of materials engineering that you would have studied in your other courses, you would like to select these features with some physical basis. You don't select the features randomly. There has to be a physical reasoning behind why you select these features. Now, I will also say that maybe this data set will have a few null entries. And the reason I am saying that is one of the things you have to do when you are pre-processing the data is to get rid of the null entries or find some way in which you can handle the null entries. So I put in this sentence just so that you keep in mind that when you are working with your data, when you are preparing your data set, you need to take into account whether there are any small issues with the data set, and that has to be ironed out. And finally, you are asked to draw a flowchart for your approach to this problem. Personally, I find the use of flowcharting or the use of pseudocodes very useful because that gives me a very visual way of figuring out how I'm going to approach the problem. So that's why the ability to draw flowcharts when you are writing this type of scripts can actually be quite useful. So let us work through this step by step. Let's break down the problem physically. So we are talking about liquidus temperatures, meaning that we are talking about melting. So going from the solid state to the liquid state. When you think about this process, in case of an alloy, the melting does not occur at a single temperature. It is going to occur over a range of temperature. So your onset melting is where you have the solidus temperature. Once you cross the solidus temperature, some of the alloy starts to melt and the rest of it is still there as a solid. And of course, as this process occurs, you will have relative changes in terms of the composition of the solid or liquid. And eventually you reach the liquidus temperature beyond which your alloy is now going to be 100% molten. You can also think of it from the reverse perspective when you think in terms of solidification, that you are starting with a molten liquid which you are freezing. The first temperature you hit as you are cooling down is going to be the liquidus temperature, where the solidification is going to start, and as the solid starts forming, the concentration of the liquid also starts changing, and then eventually as you go through the solidus temperature, all of the liquid is now frozen. Now, of course, if you want to think it from a solidification perspective, you have to keep in mind that you are doing extremely slow cooling so that you do not have any significant undercooling. But if you think from it in terms of melting, you have to think that when you are melting the material, you are going through a process which involves breakage of the bonds. Similarly, if you look at it from the other perspective, if you are thinking in terms of coming to the liquidus temperature by cooling during the process of solidification, you have to think in terms of formation of the bonds. But let us just look at it from one perspective for the purpose of this example, and let's just look at it from the perspective of melting. So when you are melting, that involves breakage of the bonds, and so your lattice structure starts getting lost, and therefore any of the features that you are going to select must be something which reflects the bonding, the strength of the bonding, the nature of the bonding, and so on. And at the same time, as this process is taking place, the composition is also continuously changing. Composition of the liquid phase and the composition of the solid phase, they are also continuously changing. Now, if you look at the alloy system and start moving towards the pure component, meaning the basic element, then what you will notice is the melting temperature is going to move closer and closer to the elemental melting temperature, and eventually, instead of having a solidus and a liquidus, you'll have a single melting temperature. So that is the physical picture. So whenever you're setting up the machine learning models, try to start with a physical picture of the problem, because it is from the physical picture that you will start getting the insights. Now, if you think in terms of the bonds that are forming, they are going to form between different atoms. How are the atoms going to be organized inside your solid material? That is something you will have to think of. So that comes from the crystal structure of the material. And what determines the crystal structure of materials? We have already discussed concepts of valence electron concentration while talking about the Hume-Rothery rules. So something like a VEC, or your valence electron concentration, can give you an idea of what crystal structure is. This is basically a consequence of the bonding. Then you can also think in terms of elastic modulus, because we have also discussed a little bit when we were talking about Eshelby's model, that the elastic modulus also gives you an idea about the force that is needed in order to break the bonds. You can think in terms of the elemental melting temperature. After all, if you think about it, the bonding is going to simply adjust the melting temperature with respect to the elemental temperatures, right? And then finally, you want to think of something like cohesive energy. Now, in terms of the cohesive energy, we have discussed a little bit about how binding takes place. So if you think along the concepts of the universal binding curve, you will know that the cohesive energy can be computed by using the formation enthalpy, which in turn you can calculate from Miedema's model. So instead of having the overall cohesive energy, you can simply use Miedema's enthalpy as one of the features and the elemental cohesive energies as the other feature. Elemental cohesive energies values are going to be quite easily available. In fact, if you look somewhere in Kittle's book, in the second chapter where he discusses crystal binding, you will have a table of cohesive energies of the pure elements. So these would be some of the features which are going to be really useful. Now the ones that I have mentioned over here in red, this is what you can take as composition average values, and then whatever I have put in blue, those are the calculated features. If you look at the cohesive energy of the alloy itself, it is actually a combination of composition weighting and calculation, which is why I have put that in purple. So the composition weighting comes because if you look at the expression for the cohesive energy for your alloy, so if I write the cohesive energy of the alloy by ECOH alloy, then this is basically the EA, which is the cohesive energy of the element A, plus the cohesive energy of the element B, and again for each of this you should have the composition weights associated with it, and from there you will subtract whatever the delta H value is. So this is how you get the cohesive energy. So you can see that you will get a composition weightage term and you are going to get an enthalpy term in there. So the main takeaway message here is that when you are trying to do the problem solving using materials informatics, you need to come up with a physical picture of what you are trying to describe, and you need to select your features accordingly. Once you have your features and you already had the basic data set which had the inputs in terms of the alloy compositions and the target values in terms of the liquidus temperature, it is now time for you to start structuring the data set. So you already have a given data set which has the alloy composition and the liquidus temperatures. You have already now figured out which type of features you would want based on the physical basis for selection of those features. So now it is time to structure the data set. So the first thing you want to do is you want to get rid of the null entries over here. So you get rid of the null entries. You now have your input conditions, which is the alloy composition. You have the features, which is going to describe your machine learning process, and then you have your target value, which is the liquidus temperature. So if you look at the process, the first step is dropping the null values. The next step is to add in the input and the target values. So in this case, the input is basically going to be the alloy compositions, and then the target is going to be the liquidus temperature. So once that is done, you have to fill in your features. So this features comes from the elemental data set that you can use, or you can simply put in the actual calculated values using the composition based feature vectors. And after that, you can pull up the thermodynamic parameters, whether that's the medium of formation enthalpy, cohesive energies, and so on. So these are essentially the ones that you are calculating based on some physical principles. So when you put all of this together, your data set is now ready. So the problem we are trying to look at is to predict the liquidus temperature. And so for that, let us start by looking at how do the shape of the liquidus curves vary. So if you take a phase diagram, for instance, here we have got a aluminum silicon phase diagram, you will see that this liquidus curves are varying in a fairly regular manner. But at the same time, if you look at the two different liquidus curves, you will see that this curvatures are actually changing. If you look at some other material like a silicon germanium, for example, you will again see that you have the liquidus curve which curves pretty steeply, whereas the solidus curve is not curving that much at all. And then again, you will have, if you look at other systems, in this case we are looking at the nickel silicon system, which is a fairly complex phase diagram. Now you can see that you have an assortment of different liquidus curves. Some of them are sloping very steeply, and then the others are not. So when you are actually going to set up the machine learning problem, you have to ensure that you will be able to capture all of these different shapes. In other words, you have to ensure that you should have some part in your machine learning architecture which is going to capture this nonlinear changes as you change the alloy concentration. So you might actually want to take up with a process which has got some kind of a nonlinear activation function built in there. You always want to start simple, so I would maybe start with a polynomial regression, because if you look at the shapes of the curves, you will see that it looks like this is something which can be fitted using polynomial functions. So I would probably start with polynomial regression, and if I do not see good results in approximating the liquidus temperature, I would then start jumping into other more complex models like neural networks and everything, where I can actually start fitting in the nonlinear activation functions. So while I would try to start with the polynomial regression, you can please feel free to use other models. There is nothing sacrosanct about using one specific model, but then it's always a good idea if you can start in a simplest possible manner, and then if the simplicity doesn't solve your problem, then you start adding in complexity. So this is basically how I would set up the problem. Now coming to how we visualize this by drawing flowcharts. The advantage of using the flowchart comes even before you start doing the problem solving. And I would urge you to think of this type of problems as peeling an onion. So essentially what we do is we will keep on adding layers of complexity. We want to start simple, and then as we get a grasp over the simple concepts, we want to keep on adding layers of complexities. So our starting point would be just to list the main functions that is required in order to address these problems. So that means the main functions would be preparing the database for the machine learning problem, loading the data, splitting it into training and testing data, and then doing the cross validation, and finally doing the evaluation and tuning of the model. So the first step is preparation of the database, which we have already discussed in great deal. So you want to remove the null entries, And once the null values are removed, you want to add in the features, whether those are the composition based feature vectors or the calculated features or a combination of both. So this is basically how you would start. You would read the provided data, you would import the CBFE and the data frame and everything. You would want to then drop the null values, read the number of rows, so that gives you an idea of the volume of the data that you are working with, and then you just want to set up a counter. After that, you will go ahead and calculate the features as a function of the composition. So this is really where the CBFE is being done, and then you want to add this to the database. So along with the CBFE, you can also add in the calculated values at this juncture, and then when you are doing it, you want to essentially do a loop. So when you set up this counter, that gave you the means of creating a loop within which you will be adding in the different features for every single row of your database. So once the loop is ending, your database is now ready. After that, you want to move into the next step, which is doing this testing, training, validation, and optimization. So now that you have your data set, you want to split that into two parts. There would be a training data and a testing data. So you will train the initial model using the training data, and then of course for training you need to have some parameters, and you have to do extensive cross validation in order to ensure that the model that you are training is actually an appropriate model. It's not something which is getting overfitted. So once your cross validation is done, now you have a set of optimal parameters, and then with that you have got your retrained model. And with your retrained model, you will now go ahead and make the predictions for the inputs in the testing dataset. And from there, you will get an idea that what is your fitting score when it comes to the training data, and what's the fitting score when it comes to the testing data. So that is how you will basically do the final evaluation of your model. Now, when you are doing this, ideally you would want to have the R-square values for your training data and testing data very close. If you have very nice R-square, maybe you get something like 0.98 or 0.99 with your training data, but with your testing data you might be getting 0.66, then that's a very clear indication that you are force fitting the data when you are training the model, and so you are losing out on the generality by doing a lot of overfitting. So that these are the things that you now want to take care at this stage. So when you are doing this, you should have an idea of the appropriate classes and functions which are required for doing the cross-validation, so that you can call them in your script as and when needed. So this is basically an overview of how you will set up a machine learning model. Now, once your machine learning model is set up, the next part is going to be to assess the model properly and then do the model interrogation. So for that, we will now look into a couple of different examples and basically see that how different researchers are approaching this type of problems.